So we'll resume our scientific talks now. So we had navigated to the world of quantum mechanics already, and hence the stage is all set for the next special lecture by Professor D.D. Sharma of IISc. He'll be talking about the miraculous world of materials. I request Professor Bhattacharya to please introduce the speaker.
Good afternoon. We will now have Professor D.D. Sharma, who is popularly known as D.D. You know, he does not really require any kind of introduction. His full name is Dipankar Das Sharma. Some of you whom do not know this for you. You know, he's I don't know whether he's a physicist or a chemist, but his areas of research encompasses very large number of scientific domains. Even if he does not require any formal introduction, but for the benefit of the younger section of the audience, I would just tell you about him. You know, he was a brilliant student, had high accomplishment right from his school education, and was an undergraduate student in IIT Kanpur in the integrated master's course, where he obtained his 5-year integrated master's in physics in 1977. Then decided to head south and enroll for research at the Indian Institute of Science, Bangalore, and where he secured his PhD degree in 1982 under the tutelage of renowned chemist Bharat Ratna Professor C.N.R. Rao. Then he worked as a research associate in IISc initially, and then moved to overseas in Forsung Centam, Ulik, as a guest scientist in the year 1984. Then he returned to Indian Institute of Science as lecturer and subsequently rose to the rank of professor. I think he had, you know, so many awards. I cannot, you know, even mention them. It's too long for me to talk about. He's the Fellows of All Academy. I will just mention the notable ones. Santi Sharu Bhatnagar Prize, INSA Young Scientist Medal, UNESCO Biennial Javed Hussain Prize, Materials Research Society of India Medal, Sir C.V. Raman Award, G.D. Birla Award, IISc Alumni Award, FICCI Award, TOAS UNESCO Prize in Physics, IIT Kanpur Distinguished Alumni Award, H.K. Firodia Award, Knight of the Order of the Star of Italy, and he's also recipient of Honorary Doctorate of Uppsala University, Sweden. He's, as I mentioned, he's also, you know, fellow of the American Physical Society and fellow of the Society for the World Academy of Sciences. He holds numerous adjunct honorary visiting professors, too long for me to say, but all I can tell you, he's one of the most prolific publisher in the field of physics, chemistry, and material science. I think I was given some information by my colleague Bijay. I think that information, if I tell, that will be actually wrong. You know, it says he has 480 scientific publication, but his actual number of publication is somewhere around 720, maybe by this time 725. And his citations exceed 27,500, and H index is 87. Just to give you a measure of the level of activity DD has, and he's publishing almost, every week a new paper. So with these few words, would like to hear from DD. Floor is all yours.
Yeah. Thank you, Professor Bhattacharya, for that embarrassingly long but very kind introduction. I've always maintained that, for example, in a marriage, the beauty of the groom should never surpass that of the bride. Similarly, there's a theorem in seminars: the introduction of the speaker should never be longer than the talk itself. And we were about to flout that, and I got worried. And then you lifted up this sheaf of A4 papers, which Vijay had given you. So I was really seriously think of coming onto the stage and stopping you. Jokes apart, it really gives me great pleasure to be coming here and talking to you about what I have announced as Miraculous World of Materials. I'll not be talking about my own work, but it's basically for the young people in the audience, trying to say why materials are not just important, they're of course important. As the saying goes, anything that is not material is immaterial. And given that fact, of course, materials are extremely important. As you would know that the importance of it is actually can be gauged from the way we also term or mark different parts of different epochs of human civilization. For example, human civilizations are marked by the materials that that particular civilization based their livelihood and every other aspect of. Like you have heard of Stone Age, stone being the material that was being largely used, then Iron Age, Bronze Age. Presumably we're living in what we call the Silicon Age today, driven by all the modern technology that are built around the silicon technology. So materials have played very important roles. But setting aside the question of importance, they're also extremely fascinating. They're fascinating because they hold out spectacular properties and they're amenable to being influenced and extracting newer properties and very often unexpected properties that are then go back to contribute to the development of the society and the civilization. So I'll be trying to give you snippets and snapshots of such cases, not necessarily trying to develop one particular theme, but make a garland or a bouquet of collection of spectacular properties of materials to tell you why materials are exciting. And, no, that's the wrong direction. Okay, so I start with this particular example. It's of a material that actually was discovered quite a while ago, several decades ago. And this is called the superabsorbent polymers. What you're seeing on this Petri dish are some nondescript white polymeric material. And incidentally, this is something that is close to Professor Bhattacharya's research activities in some more refined manner. But what I'm going to show you here is what happens when you take, okay, not that way, yeah. These are also called diaper polymer for some very specific reason that will be obvious. We took that polymer and we just poured water into that flask. And you saw the amount of water that we poured. And now if you turn it over, you find that the entire water has completely vanished. Basically, that little bit of polymer that was at the bottom of the beaker that you saw is able to absorb and hold back the water, which is something like 10 times or 20 times more than itself in volume. These are extremely super absorbent water, and that's why they're called the diaper polymers, and they have played very important role in many, many applications in life. So these are the kind of surprises that all kind of materials gives rise to. The next example that I would be taking is of these organic light-emitting diodes. This particular slide was included when I started giving these talks about 10, 15 years ago. Then it was a futuristic material. People who are talking about, normally all semiconductor materials that you know about or knew about are based on mainly silicon, but something in gallium arsenide, indium arsenide, all inorganic materials. They're very good. They're very good in terms of the mobility. They carry electron and holes around very, very fast. You can combine them, control their properties, and that's how you make all the devices that you use all the time. But organic materials can also be semiconducting. But they have one advantage. The organic material has one advantage that you don't have in the inorganic materials. Organic materials are flexible. But the problem of using organic material as semiconductor is because they have lots of defects. You cannot, the flexibility, the price that you pay is that they have a lot of defects which come in the way of these electron holes that have to run around to give rise to semiconductor device and give rise to the properties that we want in a controllable fashion. You cannot control it because the defects cannot be controlled, and their behavior or their impact on the electrons and holes are absolutely unpredictable, and that's why the semiconductor devices from organic material was very slow to develop. But as you know now, that actually organic materials are being used for many, many semiconductor applications. For example, organic light-emitting diodes, which are routinely used in many display in this laptop, for example, or in a mobile screen. And in fact, it is thought that you'd be able to have fully flexible the device's display, where you can have a display that you can roll up, put it in your pocket, go away, and then you go somewhere, you open it up, and from the internet, you download all the information. You have the newspaper, you have the article that you want to read, any scientific article, or what have you, or do any kind of application. So completely flexible organic materials leading to every kind of electronic applications that you know of is a dream that is being realized as we talk about it. In fact, today you have mobiles that can be folded up, and they're all based on such organic materials, giving rise to light-emitting diodes being used there. Shape memory alloy is yet another very fascinating subject, fascinating property that is used extensively. For example, these are the stents. These are materials that you can actually collapse into very thin tubes of this kind, and then by some kind of perturbation, often it is a thermal perturbation, slightly heating it up, it expands to become a much larger tube. And this is used as stent. For example, if you have an artery that is choking and you need to expand it up, what you do is to crimp it down to this narrow tube size so that you can push it through the artery very easily, take it to the right location, and give it the perturbation from outside so that it can open up, and then the artery opens up, which was otherwise blocking the blood flow, saving your life. And this kind of materials have this very strange property and many, many applications. And in fact, the best way to illustrate that this spectacular property would be what I show in the next slide, which is called shape memory alloy, and why it has such beautiful behavior. What we are going to show is that this little spring that you're seeing over here is made from the shape memory alloy. And it's given this particular spiral shape at a high temperature, and then at room temperature, where it has actually a crystallographic transition, but that you don't perceive by looking at the shape. At that low temperature, it can be deformed. And it is deformed, and as I'll show you now, if I, just a moment. If I can, here it is. So we'll take this particular spring, and we are going to deform it as much as we want, extend it, twist it around, completely bring it out of shape so that you can't even recognize what the original shape was. And when it is completely distorted and destructed almost, then you are going to take it and start to warm it up. And once we start to warm it up, you'll find why these are called shape memory alloy, because these alloys memorize the original shape that were given to them. Such a distorted one, you gently heat it, here with the lighter, and you'll see how the spring will revive completely, and forgetting all the kind of distortion that you gave it to, and will come back to exactly the shape that it had originally. There's deep science behind this, why it happens, but it's magical that such things can happen and materials can have this kind of property. And the application of these properties are, of course, limited by our own ability to imagine application, and a few of the applications I've already shown you. Then you have these miraculous materials here, some oxide. You know, metals are metals and non-metals are non-metals. What do I mean by that? I don't know if it is still popular. When we were in school, we had to answer this question very often, tell the difference between a metal and a non-metal. And we had to draw a table, on this side metal, on this side non-metal. Metals conducted electricity, non-metals didn't. Metals were malleable, non-metals were brittle, and so on and so forth. Metals were shiny, non-metals were not shiny, dark, and lusterless. Here is a material which is powder and evidently not malleable. Malleable material cannot be made into powder, and it's an oxide, V2O3. The question is it a metal or not a metal? By all signs of it, looking at it, one would say it's not a metal, simply because it has no quality of the metal. In fact, if you measure its resistivity, asking the question of its conductivity, you'll find that it's highly insulating. Take this material, and in fact, here is the plot of resistivity. At a low temperature, it has this fantastically high resistance, 10 to the power 8 ohms resistance. But this same material, if you start to heat up, and you come to about 180 Kelvin or so, by room temperature, you see resistivity catastrophically comes down by 6 orders of magnitude, and there it begins to conduct electricity almost as comparable as copper metal. So this material, which otherwise is an extremely good insulator, just because of changing the temperature can become almost like any good metal. This is a subclass of material study, which is the metal insulator transition, which can be brought about by either pressure, temperature, or slight changes in composition, and again play a very important role. For example, you can think of immediately, if you see this, that it can be a very good temperature sensor, because if I only monitor the temperature of this material over this region, that with temperature, the conductivity changes so rapidly that if I measure the temperature of this, I can have very accurate measure of what the temperature is. That would surely be one of the applications. There'll be many other kind of applications, and in fact, a cousin of it, not V2O3, but VO2, and a few others, play also important role in photochromic glasses, using properties that's very similar to this. So these are another subclass of materials that have been puzzling us, quizzing us, and for the last 5 decades, people are trying to understand why does it have such spectacular changes in property, going from highly insulating state to highly conducting state. And not only that, it's the conductivity changes, in fact, magnetic property changes. Here it's antiferromagnetic, and it becomes a paramagnetic one. Of course, the conductivity change can be even more spectacular, and it can be superconductor instead of just a metal. What I had talked about is that if you have a metal, and if you plot the resistance as a function of temperature, you know that the metallic conductivity goes down, resistivity goes down, conductivity goes up, simply because as you lower down the temperature, the atoms decrease their vibration. These vibrations are normally the ones that are scattering the electrons around and contributing to the resistance, but lowering the temperature, that scattering goes down, and so conductivity increases or resistivity decreases. But there are materials that become superconductor, where at a certain temperature, a finite temperature, suddenly gets into a state where there is no resistance. In fact, today in the exhibition, there was a demonstration of one of the spectacular property of a superconductor, not just going to this zero resistivity state, but the fact that it shows Meissner effect. And Are any of those, I don't know if those volunteers are here. I had a wonderful discussion with one of the volunteers about this. And that is, I'll skip that demonstration because that was already shown in the 2 days in the hall, where you put a superconducting material on top of a magnet and it floated. And this, of course, can be used for many, many different purposes. One of the purposes that even that young lady who was explaining this phenomena talked about maglev train, where if you have a material that is superconducting, on top of that, you put magnets, they repel each other so they can make the object on top float so that there's no friction, and by giving very small amount of force, you can make the train move very fast, straightforward, because most of the power spent by vehicular movement or trains or any other kind is actually coming from frictional forces. And that frictional forces will not be there if your train is levitating altogether. These are all very exotic material, V2O3 and stuff like that. Do I have exotic property from very simple materials? And this is also well known to us that think of soot, carbon. Carbon, which you used to think of as just Fu form, like graphite and diamond, two forms of carbon that you are very familiar with, over the last 30 years has really exploded into many different forms of carbon. For example, the three-dimensional form of carbon, 3D, can be either graphite or diamond. But from this graphite, if you just rub it on paper, you can take, these are very layered structure of carbon atoms connected this way. You can get one single layer out, which would be then called graphene. The reason you give it a different name is because this has property that is very different from that. Though it's nothing but a single layer out of this graphite, but this brings up a completely different property. And this has slowly opened up over the last 30 years. And as of now, in the last 3 years, some spectacular flexibility in making materials of newer kind, which is what I'll be talking about shortly. But these materials, and you can take this graphene, for example, and roll it up and connect it together to make a nanotube, or you can make another form of carbon, which is these fullerenes. There's a whole class of them, C60, C70, others, and they have all very different properties. Fullerenes play a very important role in many kind of photovoltaic applications. Carbon nanotube and graphene, I'll just spend 1 or 2 slides to tell you the kind of spectacular properties that one didn't expect out of simple carbon, but they exhibit that. For example, if we talk about the strength of this carbon nanotube, the nanotube that I showed, it's one of the strongest material that we know of. It's basically, you can take, if you could make one nanotube of 1 square millimeter size. A square millimeter is a very small cross section, and that kind of a wire, if you have, you can hang from it 6.4 tons of weight. So you can use a 1 square millimeter cable to lift up 6.4 tons of weight, which is absolutely amazing. There's nothing that can be stronger than that. In fact, this also almost makes one think that we can realize one day what Arthur C. Clarke had anticipated long time back, that we'll have space elevators where you'll have these extremely strong fibers. He didn't know that one day carbon nanotube can fulfill that dream, which can take a huge amount of weight, and space stations can go up and down along that, because that would be much more economical, because energy consumption would be much less than sending a rocket out, where the rocket, the most of the fuel is consumed by carrying the fuel itself. And that's why that's not economical, and one may be able to make such sky stations up there by using space elevators using the carbon nanotube. We're not there yet. We need many, many innovations to be able to actually realize that dream. But certainly we now have a material which we didn't even 30 years ago that can have the required strength of lifting such weights. To compare that, just to give you an idea, the high carbon steel has in some units of measuring the strength, which is the normal thing that you use in all these big cranes, etc. The big cable that's lifting up the weight is made from this high carbon steel, and that has, in these units, it can be picking something about 154, where the specific strength of the carbon nanotube that I'm talking about is 48,000 in the same unit. So it's many, many times larger than the best things that we have. And these nanotubes are being used already for their strength. For example, in lightweight materials, in aircrafts, in tennis rackets, and many other cases already used. But then you can make these carbons. The carbon is anyway a very light material, but you can make it very light, much lighter, by making something called aerogel. Aerogel is a material that looks like a solid, but actually is full of voids. It's essentially trapping void by having interconnected structure of some atoms that give it a shape, and it looks like a solid. But you can see how light it is, almost like air, such that you can have it suspended on these very thin fibers, which cannot take any weight. So this is possibly the lightest material, solid material that is known. Of course, here the definition of solid is it's not a dense solid. It's basically trapping void by making a network of atoms. And they can, incidentally, I mean, this one has huge mechanical strength. You can put a lot of weight on it, and it will not collapse. So you have very lightweight material that can support very large amount of weight and making it very, very efficient. Mobility is another. I already mentioned it in the context of semiconductor devices. One of the most important criteria for very efficient devices is mobility. What do I mean by that? Mobility, as the name suggests, is the ability to move something. What we're talking about of moving in this particular case is electrons. And electrons, of course, move because I apply a potential difference across. So the question is, if I apply a potential difference of, let's say, 1 volt, after 1 second, how much distance an electron can move? And it depends on the particular material. It's a material property. You'd expect that it would be very good when you have a metal, because in metals, you know electrons are moving freely. And then, so let's make a racetrack, and we'll put different materials in these racetracks and put a 1 volt, let's say that's 1 centimeter long, and we'll put voltages across 1 volt. After 1 second, we'll see how far they have gone. After 1 second, if I have, they'll go different distances, so different materials have different mobility. Exactly the distance I'll measure in centimeters, and that will tell me the mobility of the material under the potential difference of 1 volt measured after 1 second. If I do that for silver, which is one of the very good metals, the electron would have run 56 centimeters in 1 second. So you can see that it is a very good metal because electron can go that far very rapidly. If you take silicon, it actually goes 1400 centimeters. That's why silicon is the preferred device material. You can have electrons go without being scattered very rapidly under the same potential of 1400 centimeters. There are more expensive semiconductors which would do even better. Indium antimonide will go 77,000 centimeters. And carbon nanotube will go 100,000 centimeters. And graphene that I talked about, it will go almost 2 kilometers. In 1 second, the electron will run almost zip across, just with 1 volt application, across a 2 kilometer stretch, electron will go from one end to the other. So you can see how much the mobility can be affected by choice of materials, and that tells you how the application can evolve and give you extraordinary properties, extraordinary ability as you come to these carbon nanotubes and graphene, among other things. These nanomaterials are already actually transforming the world. These are lotus leaf. All of you know about it. It's a self-cleaning. The water droplets form these beautiful droplets, spherical-like, because they don't like to wet the leaf. They try to avoid contact with the leaf, and they make these spherical droplets. And they roll off very easily. As they roll off, they pick up these dirt particles that are sticking to the leaf, and therefore the leaf becomes clean. It's called self-cleaning mechanism. In fact, this is what happens. This is because of either the structure or the chemical property. The water doesn't like to be in contact with that, and so avoids contact, making the contact as small as possible. One of the applications that people think of is to have this kind of coating on, for example, the rear view mirror that is outside of your car, because at the time of rain, Everybody has seen how difficult it is to see anything on the backside because the water droplets are sticking to your mirror. If your mirror would be coated with this kind of material, then these will just roll off instantaneously and will not stick, because they don't like to stick. They avoid sticking. And therefore, you'll be able to see even in the rain, even with droplets, because they're not sticking all the time, falling off. In fact, you can think of it exactly in the opposite limit. What would happen if this water droplet loves contact with my material? This is called superhydrophobicity. That means that hydro, the water, phobia means not liking. This particular material on which I have put the water droplet, it hates water, and that's why it's spherical. If I have superhydrophilicity, that I love water, then the water droplet will just stretch itself to maximize the contact. In this limit also, again, your mirror will work, simply because now you have a continuous layer of water across it, and it's not droplets that's sticking, and again, you can recover the visibility. Those are not the only applications. There are many other applications, but I'm just giving you instances that you can relate to more easily. But you can have also beautiful this color. This you know, this is opal. And this color is actually, and also similar colors that you know of on beetles, peacock's feather. Those are not real colors. Those are apparent colors. What do you mean? That if you go very close and look at it under microscope, you'll find that all these things have structured material, and those materials themselves don't have any colors. For example, if you take an opal or this insect wing and crush it completely and look at it, you'll find no color there. The color is not the material property, it's the property of the way the material has been organized. That gives rise to the impression of color by reflecting and refracting and diffracting light in particular way, giving rise to the colors that you see. Peacock feather is a good example where there is no color to the peacock feather. You can take a peacock feather and start to split it out, and you'll see each strand is looking like black with some structure on it. But when they all come together, you get this impression of the color. One of the application of that is that now I can think of putting this kind of metastructure that we talk about of material together such that it will interact with the light in a peculiar way, such that the light, when it will come, it will avoid getting into the material. This is my material, which has been given a particular structure. Light is coming, avoiding to go in, and then continuing like this. The consequence of that, if I now look at it from this side, I will see everything that is on the other side of the material, because the light coming from object on that side will come around it and come to my eyes, and I'll see that object. That means that this particular object will be completely invisible to me. So people are trying to make structures such that it becomes invisible, and that has a lot of material science, not only the structure, but the choice of the material and how it interacts with photons become very important. And this is a very active area of research again. This was again illustrated, so I'll not be talking about it in the demonstration hall today. In macroscopic world, just in one sentence, is that if I take a red material, whatever that be, or a golden material, let's say gold, a large piece of gold, and I make it into smaller and smaller and smaller and smaller piece, it will always remain red. But if I take this very small and get into really sub-micron size and start to break it up, there will be a regime where, when I'm in the nanometric regime, the color of the material will actually begin to change. Here's an illustration. All these have different size cadmium selenide nanoparticles. The color that you're seeing is actually scattering color, not real color of the material. What we are going to do is to shine UV light on it, and you can see that cadmium selenide, though the material remains the same, changes the color that comes out of it drastically, spanning the entire range of visible color. Therefore, you have control of all possible colors. You can combine them to make white light for lighting, like this, or display, like in the laptops or on your mobile. And they're already being used. This kind of quantum dots are now on your TV screen. High-definition TV screen are using indium phosphide quantum dots to give rise to real good color purity and extreme efficiencies. Now, also, because of this nanoscience becoming so important, different tools have been discovered with which we can manipulate down to the atomic size. And one of the tools called the STM, scanning tunneling microscopy, which in certain mode is exactly like a finger, but a finger so fine that it can pick up an atom and put it wherever it wants, and arrange atoms at will, and also study the property of atom at that atomic scale. Think of it as a very fine finger that can do that. In fact, this picture was shown, one of the pictures that was shown was created that way in a previous talk. But here you can see here in kanji character, by putting iron, each of these blip that you're seeing is an iron atom on a background of copper. And in kanji character, what is written means atom. Similarly, carbon monoxide molecules have been arranged on a platinum background, making a nano man. Or you can put these dots of xenon atoms on nickel, and there's a trade secret. We will not tell you the name of the company that arranged this, but you can read it yourself because it's written there. And this is already has been shown to you that this was actually created by picking up individual iron atoms and placing them one after the other in a circular pattern on a copper to create this coral, quantum coral, that has peculiar properties. And this ability to control at the smallest size is, of course, driving the computational power. For example, when we started our studies in 1971, 1974, around that time, each transistor, the smallest transistor that you could make was 10 micron. 10 micron is really very small. It's 0.01 millimeter in size. And you could pack in 3,500 of those transistors to make one CPU or a processor that was called 8008. And that you can see how the transistor size kept decreasing over the years, coming down to 180 nanometers by 2000. And then by 2014, starting from 10 micron, it's at 35 nanometer. And in fact, now today the size of the transistors are down to 5 to 9 nanometers. And you are packing in billions of them. And that is why the computer power is going up so fast. But that has a problem. One of the problems that we are really tackling with is the fact that when you pack in so many transistors, each transistor is dissipating energy. And so that these are getting very hot. One of the Moore's law that said that the transistor power, the number of transistors that would be packed in, you can see per chip, will be increasing logarithmically. You can see that here is a logarithmic scale, and in time, linearly, it's increasing. But that also is leading to overheating of the chips. In fact, very soon, if you don't do something, in under few years, it is expected that if I didn't cool down the chip sufficiently, it will reach the temperature of the sun. So much of heat dissipation will take place. And that's a tremendous challenge that is trying to cope with this heating problem. In fact, this is the computer that we had when we joined, me, my wife here, in 70s, early 70s, IBM 360. Look at the size of the computer. It filled 2 rooms. There's the size of the operators. That had about 20 megaflop of computing power. My laptop has 7,000 megaflop of power. It had a 8 megabyte of RAM. The laptop today that I use has 32,000 megabyte of RAM. It had 1 megabyte of main storage. And I think there's a mistake here. It should have been a bit more, I think. I'll check that. But now we have 1 terabyte, 1 million times that size. And the size-wise, if you look at it, here is the first model of a hard disk that was being shipped. It had a 5 MB storage. It needed a special aircraft to be transporting it from where it was made in IBM to the location where it would be used. And today, of course, my mobile has 1 terabyte, 1 million megabyte of size, and fits into my pocket. And that's the power of nanoscience, where it has taken us over the years. Nanoscience is playing havoc in every field. For example, people are making nano cars. These are very clever chemistry of making this molecule that you can see. You can see this molecule has the wheels here, and in fact, these are such that they can rotate. This part of the molecule can rotate around that bond. under certain stimuli. And if the stimuli is correct, if I put the wheels all in the right direction, the car can move forward or backward if I reverse the stimuli. In fact, I'll show you an example of this real movement. And this is, of course, the cartoon. Here is the picture of the molecule. And I'll show you actually the molecules. When I put the wheels pointing to the same direction, that means they rotate incoherently, you'll see the molecule will move. It will start from somewhere lower in the frame and keep moving up and end up there, which let me hope that I can get it right. I'm never sure how it works. OK, it will work, it looks like. And you can see. No? No. Oh, media not found. Sorry. I'm sorry that this media not found because I had to copy to another. So basically, it moves from here to up there, and that movement has been tracked here. I can put the wheels in such a way that when these two wheels are trying to push it that way, this wheel is trying to push it the other way, which means that the car will not move at all. And the video would have shown that the starting position is here, the ending position is here, and all the points, if I tracked, it would have looked just like that, not moving at all. If I put this side in this direction, the wheels, this side this way, you can see that under stimuli it will just rotate. And that's what happens, that this molecule will be largely rotating, moving a little because it will be slipping, but it will be largely rotating and coming there. So these are the kind of controls that you can have at the nano level or with these molecules and many other possibilities. But I promised you that when you have come to the nano level, we did not anticipate at that time, but it's now giving rise to new definition of materials. Materials which I cannot even tell you what that material is that is showing the property, but we have extraordinary property. What do I mean by that? These are the interfaces, heterostructures, multilayers. Let me define for you what is an interface. Interface by itself is not a material. If I take a material A and if I take a material B, and if I put them in contact with each other, that defines an interface. Interface is the layer at which two materials meet each other, which has absolutely no dimension in the perpendicular direction. And if you were to ask me what is the material at interface, I can't tell you, because interface on one side has B, on the other side has A. And interface itself has nothing. But the interface is defined because I have B on one side, A on the other side. Why I want to do that? Because remember, the interface will not be there if I put A on both sides. Okay? So does the interface have some property? Let me show you two oxides, lanthanum aluminate and strontium titanate. I'll make them into an interface like that. And this is a real picture of transmission electron microscope. This strontium titanate part, on top I have put 6 layers of lanthanum aluminate. Each of these dots is an atomic column that you can see, and the interface is very clearly defined here. That's the interface. I'm going to measure the property of this. I know the property of strontium titanate. It's an insulator. It's a wide bandgap insulator and non-magnetic. I also know the property of lanthanum aluminate. It's a wider bandgap insulator. This is a huge bandgap insulator, extremely insulating and completely non-magnetic. And when I put them together, what I can get is a very high mobility metal, which can even be a superconductor and also can be magnetic. Neither of the materials that define the interface have any property that would make you anticipate that you can have a metallic system, because it's a wide bandgap insulator and a wide bandgap insulator. But this interface happens to be extremely good metal that can even be a superconductor. And that tells you now your entire space of material discovery has suddenly exploded, because you can take all known materials of which you thought you knew the properties, but you start to putting them together, and immediately you get a new material, and at least new material property. And if you have n materials, putting 2 at a time together, you have n choose 2, n combination 2 options, and you can see as n becomes large, there's an exponentially growing material number that you can explode. And people have been doing that. And then I'll end with by saying that this interface doesn't even have to be of two different materials. I said that if you put A and A, you have no interface. And now I'm going to show you that you can put A and A together and get new properties out of it. And that is opening up further excitement in this field. For example, if I have single sheet of graphite is graphene. I've already talked about it. I take 2 sheets of graphene and I put them with each other. Now, how do I put the 2 sheets with each other? I can put 2 sheets on top of each other such that it looks like one single sheet, each atom on top of the lower sheet's atom. Or I can slide the top sheet with respect to the lower sheet and put the atoms in the whole of the lower sheet like this. Or I can fix one atom on top of the other, but rotate, tilt the top sheet with respect to the lower sheet. That means, and since angle I can continuously vary, I can continuously change this angle, and each angle gives me a new material. Do they have different properties? Let me show you how different the properties can be. I'll take the graphene sheet. If I take a single sheet, this representation of electronic structure, don't worry about it. It's basically, it has a very interesting, this high mobility behavior. But it's no good for making devices because these 2 pictures that you're showing, for making devices, we need a gap between them. Basically, all semiconductor, you need it to be semiconducting. If there's no gap, that means it's a metal or a semi-metal. In this case, it's a semi-metal. You want to put a gap together. If I put 2 graphene sheets, one on top of the other, it will look like this. It still doesn't have a gap because you can see these yellow parts and the blue parts are still touching here, shown over here. But if I apply a small electric field on this, then immediately it opens up a gap and it becomes semiconducting and it becomes a device material. So is this a new material? I didn't even change the composition, orientation, separation, anything, but applied an electric field and fundamentally the property changed from a metal to a semiconductor. And it becomes a totally different property. Not only that, so are we to call them different materials? I can take this and rotate, as I said, depending on what angular rotation I give. In fact, if you rotate them, immediately you will anticipate that it's a different material. Because when you rotate, you see that if I had one single graphene, you see these beautiful hexagons. That's the smallest unit that repeats itself. But when I slightly rotate, looking from top, you see the hexagon are huge sized. It's called a moire pattern. It is the top atom and bottom atom. Because of rotation, they go out of phase, and it's a long distance after which they come back on phase. Here, the top layer and the bottom layer have atoms exactly on top of each other. But because of rotation, next thing that I find where they're on top of each other is very far away, very far away. And this completely changes its properties. There's another Mori pattern that you can see. It forms beautiful patterns, not only beautiful patterns. It says that given one particular angle, 1.16 degree rotation with respect to the lower one, and then I apply a small voltage to inject some electrons or holes, I can have a metallic state, and there's temperature, metallic state, superconducting state, insulating state, again superconducting state. And if I give a different rotation from 1.16, just a slightly different 1.05 degree, I can have a metallic state, much wider, and then superconducting state of 2 different kinds, and then an insulating state. So just by giving slight rotation different of the same material, I realize totally different properties, and therefore new materials are being discovered out of the same old material, doing nothing to the specific atoms, but just changing their atomic arrangement in a certain way. With that, let me end my talk. Oh, you can play this game more, but I don't want to indulge your, and this is now being generalized not only with graphene, but with transition metal dichalcogenides also, such that newer properties are being discovered by arranging the 2 layers in different ways. With that, let me end by telling you that I hope I have given you a glimpse of the limitless happiness and excitement that await you when you visit, dwell, invest, dream, and harvest in the realm of material discovery. Thank you. Oh, this shouldn't be the thank you. There's something else that is coming up.
Thanks a lot, Professor Sharma. That was an absolutely mesmerizing talk. cannot appreciate more the way you presented, the range of whole spectrum of beautiful properties of materials having very scary chemical names. So I now request our director to present you a memento. So we have now come to the end of this session. We now request our registrar, Professor Pillai, to deliver the concluding remarks. Okay, unfortunately he had to leave. So in place of him, Professor Vasudha Rani, our Associate Dean Student Affairs, will deliver the vote of thanks and the concluding remarks.
Good evening, everyone. So it's a pleasure to deliver the vote of thanks for the National Science Day 2025. First of all, without the enthusiastic participation of our students who have made all the models, this would not have been a grand success, thanks to them. The list of members to thank is large. Will try my best to thank everyone. On behalf of the Science Day Mentors team, I would like to propose this. First and foremost, thanks to our eminent speakers, Professor Sanjeev Galande and Professor D.D. Sarma, for inspiring the young minds today with their popular science talks. We thank Dr. Venkateshwar Garu, District Collector, Tirupati District, for gracing our celebration. He also beautifully put that the students should work towards Viksit Bharat. Wholeheartedly, we thank all the Deputy Registrars, Engineers team, IT team, Academic team, Housekeeping team, Medical team, Security, and Dining team for their unwavering support they have provided. Definitely, we could not have succeeded in having 1,000 members from the outside of campus to inside, and they have all left safely right now. We also thank the outreach and COSA members and club mentors who have taken a lot of time in this week to work on the Science Day. We thank faculty members for mentoring and igniting the young minds every day through their lectures and scientific conversations, which is what we are celebrating today on the National Science Day. We thank every schools and colleges who visited us today and enjoyed the science. We hosted about 800 school students on campus today, and a big shout out to the students who have made the models through various clubs, volunteered to organize Science Day, and the outreach team Unnati for safely bringing school students from far and wide. So we had schools coming from Sri City and Venkatagiri, and we had colleges from Chittoor and far away from this region actually. A team of 25 members, faculty and administrative members, have invested their time to bring this event fruitful. Most importantly, without the support of our director and registrar, this would not have been possible. They have provided constant mentoring and have suggested so many interesting changes, what we see today as a big success, and we probably would like to make a blueprint of what we have worked for this year. Thank you all. Please stand up for the national anthem.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता। पंजाब सिंधु गुजरात मराठा द्राविड़ उत्कल गंगा, विंध्य हिमाचल यमुना गंगा, उत्कल जलधि तरंगा। तब शुभ नामे जागे, तब शुभ आशीष मांगे, गाहे तब जय गाथा। जन गण मंगल दायक जय हे भारत भाग्य विधाता। जय हे जय हे जय हे जय 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 हे।
Yeah, please join us for the high tea outside.